This will be the Chapter 7 lecture for first year chemistry in the chapter called Chemical Quantities. This is just a quick review of the information that we cover in the class. The first thing that we talk about is a review of counting how many atoms there are in a compound. Now for this particular problem we're just counting the number of hydrogen atoms. For number 1A we have the compound calcium hydroxide, and the hydroxide ion is in parentheses and it has been doubled, and so if you're counting the number of H's it's going to be 2 because each atom inside the parentheses is going to be doubled. The O's are doubled and the H's are doubled. For letter B, counting the number of H's is rather easy because there aren't any parentheses, so you just have 8 hydrogens because that's the subscript on it. In the next example, we have ammonium hydrogen phosphate, and there are 8 hydrogens in the ammonium ion because you have the NH4 in parentheses and it's been doubled, and then the hydrogen by itself would make a grand total of 9. In the last example, we have acetic acid. There's an H in the front and there's 3 in the middle for a grand total of 4. For number 2, for a review problem, we're going to have the students calculate the formula mass for the compound, so you just need to add up the atomic masses from the periodic table, but you need to make sure that you have the right number of atoms of each in the compound. So we have 1 calcium, we only have 1 carbon, we have 3 oxygens, and if you add up those weights from the periodic table you get the formula mass for a grand total of 101 or 100.1 grams, and that would make up 1 mole of calcium carbonate. In letter B we have 2 nitrogens because the N is in the parentheses and you can see the subscript 2 would double it, and we have 8 hydrogens because they've been doubled, and we only have 1 sulfur and we have 4 oxygens, and when you add up the weights on the periodic table you get the molar mass for a grand total of 132.1 grams in a mole. For the next compound we have C3H6O, and there's 3 C's, 6 H's, and 1 O, and when you add those up you get the answer for the formula mass, and that's, there it is, 58 grams per mole. For bromine, the Hunkelbrief, you just double the weight from the periodic table, you get 159.8. For phosphoric acid, that's H3PO4, you have 3 hydrogens, 1 phosphorus, and 4 oxygens. When you add up their weights from the periodic table, you get the formula mass of 98 grams. And the last one is dinitrogen pentoxide. You have 2 nitrogens, 5 oxygens, you add them up, and you get an answer of 108 grams per mole. Now this idea of formula mass is very important because on the next slide we're going to do conversion problems just like we've done in previous chapters. We're going to convert the grams of SO3, that's sulfur trioxide, into the number of moles, and you'll have to use the formula mass for the conversion factor on the bottom. We always use 1 mole on top, and then you can cancel out your units and get your final answer for the number of moles is 10.4. For number 4, again, this is just review problems of conversions. We start with a given of 18 moles. You put your little times line. The special number for moles is always going to be 1. That needs to go on bottom to cancel out the units that were previously on top. And now you have the molecule's special number, which is Avogadro's number. You cancel out your units and you multiply it out. Now you can have this answer 2 different ways in my class. I don't care if you have it as 108 times 10 to the 23rd, or if you want to write it properly in scientific notation, it's 1.08 times 10 to the 25th. Some students don't have an exponent key on their calculator, so I let them do the shortcut method. For number 5, we're going to convert from number of atoms of helium to grams of helium. The special number for atoms is going to be Avogadro's number. That goes on bottom to cancel out the units. And grams comes from the periodic table. That's the atomic mass for helium. The units cancel, and the power of 10 to the 23rd also cancels, and you get your answer of 3.72 grams of helium. In the last conversion example, that's a review problem, we start out with 3.7 grams of water. We're going to convert that to the number of molecules. The special number for grams comes from the formula mass for water, and that's 18 grams when you add up the weights of 2 H's and 1 O on the periodic table. And then you're going to use Avogadro's number on top. The units of grams cancel out, and your final answer is going to be something times 10 to the 23rd. In this case, it's going to be 1.24 times 10 to the 23rd. So those are conversion problems using our conversion factors. A lot of them come from the formula masses or atomic masses from the periodic table. Now the meat of the chapter happens on the next slide. One of the calculations that you have to do that's new stuff in this chapter is calculating the percent composition by mass of a compound. So basically what we're going to be doing is finding the percentage of, in example number 1, we have the percentage of sodium, the percentage of phosphorus, and the percentage of oxygen in the compound Na3PO4, and we're doing the percent composition by mass. So the first step, it tells us to find the formula mass for the compound by adding together all the individual masses, and that's very easy because we just did that on slide number 1, and the grand total mass is 164 grams per mole. Now you're going to take the individual masses of the elements and you're going to divide that by the formula mass for the compound. So you're going to divide each of those individual masses for sodium, phosphorus, and oxygen by the grand total mass of 164. Multiply by 100 to get it to a percent, and then you'll have your final percent by mass. So 42.1% of the compound comes from sodium, 18.9% of the mass of the compound comes from phosphorus, and the remaining 39% comes from oxygen. Now, if you do the calculation correctly, your percentages should add up very close to 100%. With rounding, you might get 100.1 or 99.9, but if you're close to 100%, you know you've done it right. For example B, we have tin 4 chloride, that's SnCl4. The Sn element only weighs 118.7 grams. There's only one of them. And 4 chlorines weighs 142 grams. So when you add those up, you'll get the formula mass of 260.7. You're going to take each individual mass divided by your total mass and multiply by 100 to turn it into a percent. So tin is 45.5, so that means the chlorine has to be the remaining percentage, which is 54.5%. So finding percent composition is very easy. You have to find the formula mass, and then you divide each individual mass by your formula mass. The next calculation that you're going to do is going backwards from the percent data to the formula, but in the meantime we're going to look at some slides which just go over the percent composition by mass of the universe, of the Earth's crust, and of the human body. The first slide shows that most of the universe is made of hydrogen and helium, and then some trace elements. Since most of the universe is stars, that wouldn't surprise us that it's mostly hydrogen and helium, since a star is mostly hydrogen and helium. On the next slide we have the Earth's crust composition. Most of the Earth's crust is composed of dirt or sand, and sand's formula is silicon dioxide. So there's a very large mass percent of silicon and a very large mass percent of oxygen in the Earth's crust, and the remaining elements are shown: aluminum, iron, calcium, sodium, potassium, magnesium, and then some other trace elements. But most of it's silicon dioxide. If you include the entire the core of the Earth, the mantle of the Earth, and the atmosphere, the percentages change slightly. Since most of the core of the Earth is iron, iron's percent composition by mass is number 1 on the list. It's 34.6, and then come oxygen and silicon. Oxygen is going to win out a little more than silicon because you're considering the atmosphere as well as the inner parts of the Earth. And then magnesium becomes the 4th most abundant element by mass. And then you have the other ones listed on the side. You can see that most of them are rather small. For the human body, it might surprise you that oxygen is the number 1% by mass, and then comes carbon, and then comes hydrogen. Now most of the human body is water, so maybe it doesn't surprise you that it's oxygen being number 1 and hydrogen being number 3. Carbon, since we're a carbon-based life form, our DNA has a lot of carbon in it and stuff like that. It's 23% by mass. And then you have nitrogen, and again there's calcium, which is in your bones, and then some other trace elements that make your body work. So this is just interesting facts about percent composition for different things. Now we get the next part of the notes that's more important. All those little graphs that all those little pie charts that I've added to the notes aren't going to be on a test or a quiz or anything like that. That was just for their information. But anyway, the next part of the notes covers the determination of an empirical formula for a compound. So I first define what an empirical formula is. It's the simplest whole number ratio of the atoms in a compound. For example, if you look at the ratio of the atoms for hydrogen and oxygen in the formula for water, it's a 2-to-1 ratio. If you look at the formula for glucose, which is C6H12O6, that's not an empirical formula because you can reduce it to a 1 to 2-to-1 ratio. So the simplest whole number ratio is 1 to 2-to-1. That would be the empirical formula. The molecular formula would be a multiple of the empirical formula. So the empirical formula is what we're going to be calculating for a compound, and we're going to follow steps 1, 2, and 3 that's shown on the slides. And instead of going over the steps, we're going to use them in the example on the next slide. There's a little rhyme that I'm going to be following. Step 1, you're basically going to be taking the percent composition data and calling it grams of the element in a compound. So basically what we're going to be doing is we're going to be taking a sample, and you're going to have a certain percentage of, let's say, hydrogen or oxygen in that compound. And we're going to assume that you have 100 grams of the compound, so therefore if you had, let's say, 20% oxygen in the compound, and the compound weighs 100 grams, then 20 grams of it would be oxygen. So we're going to have this percent data just turned over to grams. So you're going to change your percent to mass. So you'll take all your percentages and just call them a certain number of grams. And again, we're assuming there's 100 grams in the compound. and then you're going to change the mass in grams to moles, and then you're going to divide by your smallest mole ratio. And what that'll do is it'll probably give you a whole number ratio, and if it doesn't, you're going to just multiply by either 2 or 3 or 4 until you do get a whole number. Now, in this class, since it's first year chemistry, I'm only going to have the students worry about fractions like of a half or of a third or something like that. You might have like 3/4 for a fraction or something like that, where you'd have to multiply by 4 to get to a whole number, but we're not going to see anything occurring in the homework or a test. So you're either going to multiply by 2 or 3 to get your ratio to a whole number. And this helpful rhyme is percent to mass, mass to mole, divided by small and times to a whole. It's confusing, but we'll use it in the example on the next page and it'll make some sense. So here we go. Practice problem number 1. It says an unknown compound is composed of 81.8% carbon, this is by mass, and 18.2% hydrogen by mass. So we're going to determine the empirical formula. The first thing you do is you just take those percentages and call them a certain number of grams. So that's percent to mass from our rhyme. Now you're going to change the mass to moles. And the way you do that is you just divide by the weight of the atom's atomic mass on the chart. So you just, on the periodic table. So you just divide carbon by 12 and you divide hydrogen by 1. And then you'll get the mole ratio. So the formula for a compound right now is C 6.82, H 18.2. Now since that's not a whole number, we have to figure out a way to get it to be a whole number. So we follow the next part of a rhyme, percent to mass, mass to mole, divide by small. So when you divide by small, you're going to divide by the smallest number that you see. So 6.82 is smaller than 18.2, so we're going to divide each of them by 6.82. And that hopefully will get us to a whole number. If it doesn't, we'll follow the last part of a rhyme. As you see, the answer is not a whole number ratio. We have a 1 to 2.67 ratio. So we're going to multiply by either 2 or 3 to get this to be a whole number. So the part of the rhyme that I'm following is times to a whole. So you have to multiply by either 2 or 3 to get it to be a whole number. With some reasoning, you can figure out that you have to triple it. Now if you triple the hydrogen to get it to be a whole number, you also have to triple the carbon to get it to be a whole number. Well, it already is a whole number, but if you triple one, you have to triple the other. So when you multiply each of them by 3, you do get the simplest whole number ratio of 3 to 8. Now 3 to 8 is the same as 1 to 2.67, which is the same as 6.82 to 18.2. So your ratio has always been 3 to 8, but it hasn't been a whole number until the last step of your rhyme. This happens to be propane for the compound C3H8. Now for number 2, we do the exact same thing as before. We're going to change the 42.9% carbon into 42.9 grams, and it says the rest of the compound is oxygen. Now since there's only 2 elements in the compound, we know that the remaining mass has to be oxygen, or the remaining percentage has to be oxygen. So it's 57.1%, and we're assuming that the compound is a 100-gram sample, so it's just 57.1 grams. So that's the percent to mass. Now we'll change mass to moles by dividing by the atomic masses on the periodic table. So you divide carbon by 12 just like we did before, and oxygen is divided by 16. So now we have our decimal ratio of 3.575 to 3.569, and then we'll follow the next part of a rhyme, which is percent to mass, mass to mole. Here comes divide by small. The smallest ratio is the 3.569, so we divide each of them by the smallest ratio that we have, and hopefully that'll be a whole number ratio. Now it is. It's 1.0 to 1.0, so it's a 1-to-1 ratio. We don't have to multiply anybody, and so you just get an answer of CO, which is carbon monoxide. Now on the next page, I'm going to show you that you can actually check your work, which is a wonderful thing to have in a chemistry conversion problem or something like that, a way to see if you got the right answer. So what you can do is you can take your formula CO, find the percentage of carbon or the percentage of oxygen, see if it matches up to your original problem, and then you know you did it right. So the carbon-oxygen compound weighs 28 grams. That's 1 carbon is 12 and 1 oxygen is 16. And so the percentage of carbon would just be 12 divided by 28, which is 42.9%, which matches our starting percentages, and the percentage of oxygen would obviously match up. So we know we did the problem right. And that's basically all you need to do for this particular chapter. Find percent composition and find an empirical formula. The last part is finding the molecular formula for a compound, which is very, very similar to finding the empirical formula, except you have one little step left. So a molecular formula is either the same as the empirical formula, or it's a whole number multiple of this ratio. So for example, H2O is a 2-to-1 ratio. That's not only the simplest ratio, that's the true formula for water. But if you look at the next ratio of 1 to 2 to 1, that's carbon is 1, hydrogen is 2, and oxygen is 1. This 1 to 2 to 1 1 ratio is the empirical formula for not only sugar, but ethanoic acid and also methanol. So 3 compounds have a 1 to 2 to 1 ratio, but their molecular formula is different. The molecular formula for glucose, for example, is a multiple of 6 times the empirical formula. So we're going to have to figure out what this multiple is, and that's basically the only step we have that's different than finding an empirical formula. So we're going to follow the steps that are on the screen in the practice problem on the next page. So we have our percent to mass part, so we're going to take 58.8% of carbon and change it to 58.8 grams. We do the same thing for the hydrogen percent and the oxygen percent. We take the percent to mass. We do mass to moles by dividing each of them by their atomic weights on the periodic table. So carbon is divided by 12, hydrogen is divided by 1, and oxygen is divided by 16. And I'm rounding off of each of these atomic masses to 1 decimal place. So now we have our decimal ratio for the compound. So our compound is C 4.9, H 9.8, O 1.96. So we've done percent to mass and mass to mole. Now we have to divide by small, and the smallest answer is 1.96, and hopefully this will give us whole number ratios. Let's see. Oh, it's not. It's 2.5, 5, and 1. So we need to multiply to get a whole number. So you either multiply by 2 or 3, and again with some reasoning you can figure out it's a 2. So our simplest whole number ratio is actually 5 to 10 to 2. Now, this is the empirical formula. We want to find the molecular formula for the compound. So if you go up and read the question again, it says the molecular formula mass is supposed to be 204 grams. So in order to figure out the molecular formula, we have to see if the empirical formula mass is actually 204. So let's add up 5 carbons, 10 hydrogens, and 2 oxygens. See what we get. So our formula mass for 5 carbons, 10 hydrogens, and 2 oxygens is only 102. So we're off by some factor. It's either going to be a factor of 1, 2, 3, 4, 5, 6, all the way up to 10, I guess, or even higher. On my test, since it's first year chemistry, I'm not going to go over 10. But anyway, we're off by some factor. So how do you go from 102 grams up to 204 grams? Well, again, with some reasoning, you can figure out that it's a factor of 2. So we're off by a factor of 2. So instead of our ratio really being 5 to 10 to 2, it's twice that. So our real formula is C10H20O4. And that's how you do a molecular formula. Very similar to an empirical formula, except this one little step at the very end where you have to compare the empirical formula mass to the molecular formula mass. Now I'll always give you the molecular formula mass in the problem, so if you see a molecular formula, you know you're going to have to do this last little comparison. Now we have a final practice problem doing the same thing as before. We have 40% carbon, 6.6% hydrogen, and 53.4% oxygen. We do percent to mass. We change mass to moles by dividing by their weights on the chart. And then you get your simple decimal ratio turned into a whole number ratio, which is 1 to 2 to 1. You're going to be dividing each of them by the smallest ratio, which was 3.3. So you get a 1 to 2 to 1 ratio. You could do that in your head. You really don't have to show your work on this one. It's pretty easy. Now we have to figure out how much CH2O weighs. 1 C, 2 H's, and 1 O weighs 30 grams from the weights on the periodic table. And if you look again at the problem, it says we need to find the molecular formula, and the mass of 1 mole, that's the molar mass, is 120 grams. So how do you go from 30 grams up to 120? Well, we're off by what factor? That would be a factor of 4. So instead of being 1 to 2 to 1, it's 4 times that. So it's 4 to 8 to 4. And that's the molecular formula for the compound. And that's basically the notes.